Alrighty, now types of experiments, and these are derived from this completely randomized design. And a block is a group of experimental units that are similar in some way that affects the outcome of the experiment. And block designs and experiments are very similar to stratification for sampling. Both are meant to reduce the variation among the subjects, and the objective is to compare more than two populations. Blocking also allows for a more precise overall conclusion because the systematic differences are due to some characteristic that can actually be accounted for. So I can actually say like what this medication's effects are for male versus female patients. I can say how effective is this diet for people over 40, people between 25 and 40, and people under 25, etc. So I can make more precise conclusions. And we should always block on the confounding variable. This is an intentional move, and it's not at random. The random assignment of experimental units in the blocks to treatments is carried out separately within each block, and we call this a randomized block design. So basically, I'm intentionally blocking, but then once I have my blocks, within both of my blocks, I'm going to carry out the completely randomized design. So let's take a look at an example question here. An experiment will be conducted to determine whether children learn their multiplication facts better by practicing with flashcards or practicing on a computer. The children available for the study are 40 female 4th graders, 60 male 4th graders, 56 female 5th graders, and 44 male 5th graders. After a few practice runs using the treatments, the children will be given a test on their multiplication facts. What variable should we block on? Now we have some options here, right? Because we have different grade level and we have different genders. Now, if we're measuring, though, multiplication facts and learning, I would choose grade level over gender identity simply because I would expect 5th graders to be a little bit more along their developmental progression as opposed to these 4th graders. So that would be the variable I would block on. Of course, you can block on the gender identity if you want to, but you do need to be able to justify that. So for us, we will block on grade level. So what variable should we block on? We'll block on grade level because we'd expect older students to be more, how do you say no more? We'd expect older students to be more developed in their learning. How about that? We feel as though there's more differences due to grade level than there would be to gender identity for this case. Now, if we were talking maturity, then maybe we could change it up with gender identity. But let's design our experiment. So let's look at 40 plus 60 is 100, 44 plus 56 is 100. So it looks like here I've got 200 students. And then from my 200 students, my first group will be the 4th graders, which I know there's 100 of them. And then my second group will be 5th grade, which I know there's 100 of them. Now, notice I'm not randomly assigning the 200 students here. I know who's in 4th grade. I know who's in 5th grade. So my random won't take place there. But now, from here, within each of these blocks, so I'll put a box for my block here, it's close enough to a rectangle. We'll have the flashcard method, and we'll have 50 students go there. And we'll have the computer method, 50 students go there. And same thing for the group of 5th graders, since they have the same sample size. Now, from here, I'm just going to compare my results on the test. So compare scores, and then I'll compare scores. And then, of course, I could make the comparison between the two different grade levels. But now I need to ask myself, where does my randomization method take place? So I don't randomly assign them to the different grades. They've already have that characteristic. So we're going to embed that into our experiment. So I'm going to randomly assign them to the treatment groups because I'm randomly assigning experimental units to the groups. So you can see within each block, you basically carry out the completely randomized design. The only additional step here is that you are blocking first. So we've justified our block, and now we need to talk about our randomization method. So here's what we can do, just a simple thing. There's only two outcomes. Why don't we just flip a coin? So here's what we'll do. And we need to specify that within each block, you will flip a coin. If heads, the child will get flashcards, and if tails, the child will get a computer. Repeat this process until one treatment group has 50 participants. The remaining participants will be assigned to the non-completed group. All right, do we have some element of randomness? Yep, we're flipping a coin. We've distinguished that heads will get flashcards, tails will get computers. Once one group hits 50, everyone who's left over will go to the other group, and I've specified that this is happening within each block. So that would be our randomization method there. Do we have control? So see, now we're looking at this. Do we actually have control? Which one would be the control? Maybe the flashcards, since that's not as much as a developed system, right? Computers now and websites for learning, there's more options there. So flashcards could be our control, computer would be the other treatment. So that would be the comparison of the two groups. We've blocked. We have our response variable, replication. There's enough experimental units in each group. Random assignment, we're flipping a coin. And so let's see, no placebo here. Is it possible to use blinding in the study? Why or why not? Well, let's look at the treatments. It's either a flashcard or a computer. So you're going to know which treatment you get based on which one of those two options you'd have. So is it possible to use blinding in this study? No, it is not possible to use blinding in this study, since a child would know which treatment, either flashcards or computer, they are receiving. So answer, no. Context, the children and flashcards and computer, and then explaining that no, they're going to see which treatment they're receiving, so it's not really possible to use blinding here. So go team, go. So that's an example of a randomized block design, where you block and you have whole groups and then you carry out those completely randomized designs. Now, the third and last type of design we're going to talk about in AP Stats is called the matched pairs design. And this is used to compare only two treatments. And this method reduces the variability within the sample, since you are trying to match a subject's characteristics as closely as possible. This makes it easier to detect differences within the two populations or treatments. And in fact, this is a specialized block with only size 2. So here, each block consists of just 2 units that are matched as closely as possible. And typically, flipping a coin is the easiest way to decide which unit receives which treatment. The following provides examples of scenarios. So for example, you can have one experimental unit that receives 2 treatments. This could be a before and after study, or maybe 2 different treatments where you serve as your own control. Or maybe you can have 2 separate experimental units that receive the same treatment. And this could be something along the lines of twins or spouses and partners. Or this could be 2 experimental units who are matched as similarly as possible. So for example, a male and female graduate from Texas A&M University that both majored in electrical engineering that are working at a similar type of engineering firm, and we're comparing their salaries and whatnot. So we're just trying to match as similarly as possible here. So let's take a look at an example. The manufacturers of a new running shoe Blast-Off claim that a new insole material acts as a springboard, launching the runner forward with every step. Researchers want to determine if there is a difference in the average running speed for runners wearing the Blast-Off model compared to a traditional shoe. 100 runners volunteer for the study, and each runner is given both pairs of shoes that appear identical. So there's our blinding, right? They can't tell which one's the difference. The order of which pair of shoes to record a trial run is randomly determined, and the mean run times wearing both shoes is recorded. Design your experiment and include your randomization method. So here it doesn't really make too much sense to draw a diagram just because there's only really 2 outcomes. So we can just describe this one in a written sense. So flip a coin for each volunteer. If heads, the volunteer will start with Blast-Off and then switch to the traditional shoe. If tails, the volunteer we'll start with the traditional shoe and then switch to blast off. Record the mean run times for both shoes for each runner. So you can see here this is a little bit easier just because we're conducting the same experiment 100 separate times because we have 100 separate volunteers. They're going to take both shoes, they're going to run the trial run, we'll record those times, and then we're going to see, is there an actual difference here? So the thing with match pairs is we're looking at the differences between the blast off and the traditional shoe. So I'm looking at, is this difference significant? Is the difference positive? Like, is there actually a quicker runtime with blast off, or is there a slower runtime? Now, a potential confounding variable in the study, we just took 100 volunteers. So one would be runner status, right? This would be an example of like our health. So maybe better runners would have quicker times regardless of the shoe. Or maybe this could deal with age, and maybe that younger runners are more captivated by the design, and this leads them to a false sense of speed. Although we were told that the shoes were identical, but maybe they think in their head that the blast, like they can tell which one's the blast off, and so they convince themselves that they're quicker with that one, etc. So again, just some ideas, always related to the explanatory variable. So here it's the type of shoe, and then how that would lead to what influence that would have on running time. Cool beans. So I'm going to give you a few seconds, well, for me it'll feel like seconds, for you all minutes, to go ahead and try these example problems. We'll review and then we'll stamp our key points from this lesson. So go ahead and pause the video now and take a look at these practice questions. Alright, so hopefully you were able to figure these out. Here a match pairs t-test would not be appropriate when you randomly assign the pairs together. Remember, we want to be intentional when we block. So we can see spouses, we can see twins, people who are matched as similarly as possible. So those are all good situations for our match pairs. Here, we'd want to block on athletic ability. So this would be a randomized block design. And then down here, we have sets of twins within each gender of the lamb. So we're going to use a match pairs design to compare the differences of weight gain for the sets of twins within each gender. Again, I'm justifying which design I'm using. And I'll flip a coin per the set of twins. So if it's tails, the first lamb is going to receive genetically modified corn, and the other twin receives non-genetically modified corn. Or if it's heads, the first lamb receives the non-genetically modified corn, and the other one receives genetically modified corn. Here, I'm going to compare the weight gain at the end of these 5 weeks and see if these paired differences are significant. And again, my units are matched as similarly as possible because they are twin lambs. So ideally, both of these lambs are experiencing the same conditions, have the same type of genetic makeup. So that's going to be our conclusion here of block designs. So you can see in the top there, this is a randomized block design where I block on a characteristic or a confounding variable. So the subjects are grouped in very similar characteristic groups, and then within each of those blocks, I'm going to now carry out the random allocation to the treatments and compare the results within each block. The other type of blocking, a special case where your block size is only 2, is match pairs. And so either one experimental unit receives 2 treatments, and then we compare those results within each experimental unit, or you match 2 participants as similarly as possible and then compare the differences of the treatments there. So our 2 block designs, a randomized block and match pairs design. It's going to wrap up our discussion on types of experimental design. And in our last lesson of this unit, we're going to talk about what it means for the scope of inference.